Thanks, everyone. My name is Hongfen Yu, the director of Holland Computing Center. Welcome to join HCC Kickstart. So in this section, I will introduce Holland Computing Center and go through the major facility we provide, and as well as the research conducted at our Holland Computing Center. All right, okay. Let me continue my talk. Okay. All right, so HCC is the supercomputing core for the whole University of Nebraska system. So currently we serve about 100 departments NU system-wide, and we have roughly 250 research groups and more than 1,700 users who are actively use our resource. Every month, roughly more than 7 million CPU hours has been used by our users. Aggregately, we have about 36,500 CPU cores, 23 petabytes storage, and 100 gigabits to the internet too. To facilitate GPU intensive computing, specifically like machine learning and AI type of applications in the recent years, we also have more than 130 GPUs, including 52 NVIDIA V100. Access to HCC machine is most shared and free, and the user account is created by each research group, who is typically led by the faculty member at NU system. And for any members who are associated with the research group and affiliated with NU system, and they can access most of our machines at no charge. And this necessitates waiting in the queue. In some circumstance, if immediate access is needed, and the people also can apply or use our priority access with certain fees. And currently we have 7 system administrators, 5 application specialists, 2 research personnel, 1 outreach and training specialist, and 1 web and database analyst. And among them, 8 of our colleagues hold a PhD degree. And our colleagues provide expertise for code porting, parallelization, data-intensive workflow deployment. So in the rest of the talk, I will give you a few examples about these research activities, and including the collaborations of our faculty member and HCC colleagues. So as shown in this map, you might see we provide high-performance research computing for the University of Nebraska and beyond, and other universities at Nebraska, such as Crown University. And we also work with them and provide high-performance computing support for them. Our facility most host in 3 data centers. At Holland, we have Peter Stewart Institute Data Center. It has 1,800 square feet machine room, and the power consumption is about 310 kilowatt. We have 4 full-time staff working at the PKI data center. At the Lincoln, we have Shaw Center. So this is our main office with 12 full-time staff working at the Lincoln campus. And the machine room is about 2,200 square feet and with 240 kilowatt power consumption. And we also have a machine room at the Scott Engineering Data Center. Overall, it has about 3,110 square feet machine room, and HCC use among the overall power consumption, HCC use roughly about 95 kilowatt. So we have the different machines and resource hosted at the different data centers. So at PKI, we have Crane, so which is our major cluster in support of analysis and numerical exploration. The computational power is more than 120 teraflops. It contains more than 10,000 cores and 1.5 petabytes storage. The Crane also have 52 NVIDIA V100 GPUs. So at the Shaw Center, we have the a class named RED, which most support our national funded project, including USCMS project, Open Science Grid project, and it contains over 11 petabytes of storage and over 15,000 job slots. So this class provides no interaction login account, so most is provided the usage in the national and international research communities. Our cloud computing environment named Enview, so which is an OpenStack cloud machine. It contains 440 cores and with almost 0.5 petabytes of storage. It provides the virtual machine support, and it hosts at the PKI, our data center. We also provide a nearline data storage called Attic. So the main machine is hosted at the PKI data center. It provides 3 petabytes near archive data storage. And it can be accessed via Globus, rsync, SFTP. And it also provides 25 gigabits transfer node front end. And the data on the Attic is fully replicated back to the Lincoln called the Silo, which is a mirror of Attic and provides 3 petabytes of storage and host at the Scott Engineering Data Center. We also have another storage system called the Common, which provides a transparent file system and be accessible between all the HCC storage. It is about 1.9 petabytes of storage. And recently, we also deployed our new computational class named Swan. It contains 8,320 cores, 5,300 terabytes storage, and among them, 12 nodes, each with 2 NVIDIA Tesla T4 GPUs. Again, so these are specifically to address the current GPU-intensive applications, for example, in the AI and machine learning applications. And we also have 2 high memory nodes to address high memory computational tasks, for example, in the bioinformatics applications. So in the rest sections of the Kickstart, and we will provide more details about these storage and computing resources, as well as the applications and method to access and utilize those computational facilities. So we also have some ongoing upgrade in this fiscal year. First, we are replacing our common storage with a new upgrade hardware. And recently, we also got an award from NSF CC Star program. And we propose to develop a new storage solution called NRD Store, Nebraska Research Data Storage. We plan to develop this new storage to accessible on HCC computer clusters. But meanwhile, the new storage can be also mountable by NU researchers on their laptop, on their computers, at the workstations. So in this way, we hope we can facilitate the data management and the data transferring on the research data between the researchers, their local machines, as well as HCC computing clusters. And we also plan to upgrade our Enview OpenStack cloud resource to refresh the hardware, and as well as to support modern cloud-based applications. And all this ongoing upgrade effort, we incorporated the feedback from our faculty member and the researchers in our NU system. And this effort is supported by UNL Office of Research and Economic Development, Nebraska Research Initiative, and the National Science Foundation. So hopefully then you might see more news about our hardware and the resource upgrade in this fiscal year. Okay, so as I mentioned, most of our resource is provided in a free and shared manner to all the NU students, staff, and the faculty members. And our resource maintained by our system administrations. And we provide a dedicated computing resource and also the possible extended storage and the personal effort available for a fee. And we have several research collaborative effort and leveraging our system administration knowledge as well as the domain research effort from the different faculty members. Meanwhile, we also provide education effort, so which including hands-on workshops and such like the sections you already attended this morning and also in the afternoon and tomorrow. And we also provide classroom tutorials and course support. And we also provide individual group trainings. So if your research group have any needs and would like to have a group training, please feel free to contact with us. We also provide consulting service on the research computing and storage. And we facilitate the research computing and storage solutions and also provide suggestions on the workflow and data management. And we also participate in the proposal development with our faculty member. Several extended computing resources has been offered through the national and international research effort, so including the Open Science Grid. So through the Open Science Grid, we provided the computing facility span over the 130 institutions nationwide. And we are also part of the XSEED effort, so which is an NSF project and extended from the previous XSEED project, provide the supercomputing powers to the universities and also the research sectors. We are also part of Pacific Research Platform effort and develop and provide a hyperscale Kubernetes GPU cluster for parallel computing research effort. And recently, we also got an award from NSF and joined the effort to build a national research platform. And this project is to provide all-in-one system for the computing research education resources to the nationwide research and scientific effort. So as I mentioned in the previous slides, the users at HCC is highly diverse. So as I mentioned, many research areas at NU system are utilizing the resource at HCC. There's roughly 100 departments NU system-wide, and the 250 active research groups are using HCC's resource. So active users is more than 1,700. And each month, 7 million CPU hours has been used. And this diagram showing the distribution of the histogram of usage of the different software package. So this is a very useful information for us. And then we can see the usage among the usage of different package among our users and to get a better understanding about the research needs. For example, here you might see the traditional distributed computing program use Open MPI and is still ranked #1. But we also see the package management software and also the Python related program has been increased among our users. And recently we also see the statistic type of software based on R MATLAB. The usage has been also increased. So this helps us to get a better understanding about the research activities conducted at the NU system and also tailored to our adjustment about hardware planning as well as the training activities planning. A good range of research activities has been utilizing HCC's resource. So here I just give you a few examples from the high throughput phenotyping, word for food, high throughput computational drug screen, nanoscience, smart building engineering, digital humanity, fine art, COVID-19, road and vehicle safety, and a good range of research areas. And the corresponding research effort is leveraging the research computing and storage resource at HCC. And in particularly, we also provide system administration support and application specialist support for them to establish their workflow. And some research personnel at HCC has been actively worked with research faculty members and leading to the new scientific discoveries. So next, I will give you a few examples. So first example is provided by Professor Zigangfen, and he's a professor at the University of Nebraska at Omaha, and he conducts computational method for design optimal health insurance, and studying the quantitative theoretical model to study how the private sectors responds to government policies. His interesting to study the interplay between these two factors. For example, how government tax policy and healthcare policy could interplay household and business. He used HCC's resource to analyze the large-scale national data. And the HCC resource make it possible for him to efficiently and effectively analyze massive and complex national economic data. And meanwhile, based on the analysis result, and he also designed the simulation code to mimic the economic behaviors of large-scale American household and the business. And among all these entities, and the number is large, typically is over millions, and also with a very diverse socioeconomic characteristics. And by using the analysis facilities and the simulation powers enabled by HCC, it has leading to some novel findings as social welfare, income equality, and health disparity. So next example is conducted by Professor Mohammed Hassan. Mohammed Hassan is an expert in the machine learning and AI research. And in this study, he used machine learning techniques to enhance the social media analysis and using HCC resource, in particularly for GPU. In this study, he developed a machine learning-based framework to automatically detect the COVID-19 misinformation on social media and analyze the dynamic trends of those information on the social media, and also develop multidimensional studies and to investigate the efficiency of deep learning-based natural language processing. So in his study, the multidimensional deep learning-based algorithm allowed him to identify the keywords and showing the evolution in the high frequency of this information. And so this diagram on the right side showing the word cloud visualization in tweeters and highlight the high frequency keyword. And he explained a little bit to me. And one interesting discovery, you might see those frequency are changed over time. And those word cloud showing the frequency of the keyword happened in the 2020. And you might see in the September, and when the school starts, and the keyword of the children and the schools are pop up. And also, so showing the people's emotion change and reflect on those information on social medias. Oops. Okay. So next project is conducted by the Professor Joseph Yesman and Derek Wisdom. So Derek is a professor associated with HCC, and Joseph Yesman is a professor from the chemistry. And in this collective effort, they develop a science gateway for design and optimizing RNA nanostructures. So in this joint effort, a comprehensive science gateway is designed, and a cross-link website is built, allowed scientists and the community to have easy access to the tools named the RNA Maker. And through this interface, and the scientists can easily build their models of their NRI model. And the program consists of several applications in RNA design and running on the high-performance computing centers and through the HCC. So this program provide an intuitive user interface, so let the scientists to focus on the RNA design rather than the non-trivial and tedious computing and data management of large-scale processing of the data with the tools. And through this website, and researchers can, through the user interface, and to intuitively to upload their data, conduct the computational analysis and the modeling, and then they can interactively directly visualize the result on their website. So as showing this screen capture and showing one examples, and with the two data set, and the scientists can see those directly, and also conduct interactive comparing by zoom in, zoom out, and focusing the specific area. And also the effort involved undergraduate students of school computing, and they contributed to this project through the senior design effort. And through this teamwork, the undergrad student got the training and experience how to conduct the research work and communicate with different researchers in different domains. So here, including the expertise in the RNA nanostructures in chemistry, as well as computer scientist, and also get the holistic experience to build an end-to-end workflow, and from the user interface to the front end cyber infrastructure management. So next example is conducted by Professor Huckmore and myself. So we develop advanced image analysis techniques for high throughput phenotyping of the plants. So the objective of this effort is to develop a new imaging and 3D reconstruction systems, allowed us to capture the high resolution dynamics of plant growth, and without damage the plant. And in this effort, we take the multiple view of the plants, and then leverage the 3D reconstruction algorithms, and using the computational resource, including the GPU on HCC. After we construct the detailed 3D reconstruction structures of the plants, then we can conduct the segment of the plant. So in this example, we conduct the segmentation of the panicles. And our result allowed us to get detailed structures of each individual seeds on the panicles, apart from the traditional trails, like the volume size of the whole panicles. And we can also get more detailed trails, examples of volumes, and the colors, as well as the numbers of seeds, and from our result. So in this way, we can provide high resolution and detailed trails to get better description of the plant growth, and allowed us to get deep understanding of the phenotyping of the plants. So this video give a high-level demonstration about this system. So this system, and by taking the images, multiple images from the plans, and the construction of this system is using the regular materials, and you can purchase from the Amazon or the Home Depot, and without any specialized and expensive device. And then you can get the detailed high-resolution images. However, to construct the 3D structure from the multiple images is non-trivial, and we utilize the AI and machine learning algorithms to get a detailed 3D result. So this video, now you see the 3D reconstruction in the by the algorithms, and you might see the detailed structure of the pentacles has been constructed. Okay. And we also apply this system to the plan, relative large-scale plans. And again, the imaging device is a relative less expensive, and the general labs can construct them with relative low cost. And this allows scientists to capture the images from the different view angles, okay, as shown in these videos. And once we got the multiple view images, then we upload the images to HCC machines and do the 3D reconstruction, as well as the image segmentations to get the detailed trails about the plans. So for now, we developed the different machine learning-based algorithm ranging from the different tasks. For example, from the simple task like the leaf accounting for a given plan, to the detailed 3D reconstruction of each individual tissues, like the individual leaf. So allowed us to get the detailed quantification of the plants. Example, like the area of each leaf, the length of each leaf, and also other trails. So this method allowed us to get all this detailed phenotyping, which would not allowed using the traditional technology or using the otherwise we need to acquire very expensive 3D capture devices. So the next example is also very interesting, and personally I also like this research a lot. So this research is conducted by Professor Robert Tolman, and he created some new form of media arts by leveraging the machine learning and AI. And in particular, he conducted experimental study and explored how machine learning and AI can extend the human perception, and using the algorithm of AI and machine learning to mimic the human's artwork. And the complex AI and machine learning training models is conducted on Crane system at HCC. So the new form of media arts include a neural network trained on children's artwork. So as shown in this image on the right side. So on the top, you might see the sketch for the kid, and the machine learning can take this as input and study the patterns, and then the model can be utilized utilized to generate the image to mimic the patterns extracted from the children's artwork. So as shown in the lower part of the left image, so the robotic arm can be controlled by the AI and the models and to mimic the drawings. And another example, including the machine learning generated visual as a reflection on the historical concept, and also the performance of AI written radio players. Okay. So those AI and machine learning and provide a new venues for researchers to explore the media and arts. And more importantly, this effort has been incorporated into the classroom. Okay. And Professor Tolman also trained student to be computational ask and develop the machine learning algorithms and the crowdfunding, the computational intensive workflow, and to help the student to explore these new directions. So the Crane system and the crowdfunding GPUs are leveraged in this effort, and we have set up the workflow for this effort, and also set up the environment from the classroom account, from the accounts for each individual student, as well as the workflow set up for this effort. And so this is just one example for HCC to facilitate this teaching and research effort. Okay. So apart from those specific individual effort, and HCC is also a part of the national-wide effort. So here I just give you one example. For example, we are the part of National Research Platform. So as shown on the top image, so this effort, including 3 major supercomputing centers. At the West Coast, we have a San Diego Supercomputing Center, and on the East, we have the Massachusetts Green HPC Center, and HCC is located in the center of the national and be the major hub of this research platform. And recently, UNL also got 51 million, and which could be the one of the largest award received from NSF by the University of Nebraska. And the Husk teams and leading to the role on the large CMS effort to analyze and large scale experimental data from the LHC effort conducted at the Europe. And we are also the part of the National Agriculture Producer Data Collaborative effort. So this effort is funded by the USDA, aimed to form the plan to develop next generation platform to host the agriculture producer data. And UNL is leading this effort, and HCC is a part of this effort and provide the input from the cyber infrastructure and the research computing and the data storage effort. So those are the few examples about the research effort and relate to the HCC. And all this research effort and it essentially is built on our facilities, including hardware and the software, and also the effort from our colleagues to make those exciting things happen. So you might already attend this morning sections and introduce the access and some operations on our clusters. And in the rest of the sections, when we will provide more detailed instructions about those knowledge and information. And so HCC machine is most running on the Linux cluster. So the traditional interface is provided at the Linux shell. So you might already have some experience in this morning's sections. And the user interactions most based on the text-based interface. Then you can submit your job and look at your files through those command line interface. And we also deployed an interactive interface called Open On Demand. So this is a web-based access to the supercomputing. It is provide interactive graphics user interface, and it is an open source program developed by the Ohio Supercomputing Center. And currently it's available on Crane and Swarm. And to use Open Demand, and you don't need to install any software, and only a web browser and an HCC account is needed. So here I just showing several examples of the functionality enabled by the Open On Demand. And you can use Open On Demand through your regular web interface, and you don't need to install any plugins or any specific program. And through the web interface, then you can access many functionalities from the File Explorer, so which provide the traditional interface, allow you to manage your files and download and upload your data through the File Explorer. And you also can compose your job and submit your script through the user interface. If you prefer the traditional share access, yes, this Open-on-Demand program also provides a traditional CLI interface, allow you to enter your command line and using the traditional interface. And you also can leverage the interactive desktop and also the Jupyter Notebook, provide the interactive coding functionalities. And the Open-on-Demand also provide other applications such as R, MATLAB, and more functionalities can be also possible with Open-on-Demand. You might also use our virtual machine on the NView. So NView is our virtual machine and a cloud environment, and you can create your virtual machine relatively easily. And as shown in this diagram, roughly about 5 steps, then you can create your virtual machine. And we also provide intuitive interface, allow you to select a different instance according to the different CPUs and memory requirement. And we provide multiple operating systems from Windows and to the Linux different distributions. And we also provide pre-configured configured software. And for example, like MATLAB and also the different Unix Linux environment. And you can access the VM through the SSH or the remote desk on your Windows environment. We also provide different storage options. So this diagram illustrates the different storage options provided by HCC. So around the horizontal axis, so this indicating the different speed of the file access. On the right side, you have the fast file access, and but with reduced redundancy or backup. So this makes sense once you have the high performance file systems, but it makes the duplication more challenging. So on the right end of the spectrum, so which is our work system, so which provides the fastest access to our data storage. And again, you can use our work system without any cost. And each group get a 50 terabytes quota. And there's no backup and on the work, and also subject to purge of the files after the certain time period. So next is the common. So as I mentioned, the common storage provides the access to all the HCC research computing facilities, and each group provides 30 terabytes. Additional storage you can purchase with a certain fees. And again, there's no backup for the common. And home is a media speed access storage, and individual cost for the users is 20 gigabytes, and it is mounted on single cluster. And we provide a daily backup of the home directory. So the home, common, and work is the primary storage and provide active access and mounted to the Swan and the Crane. On the left side of the spectrum, we have nearline archive storage called Attic, and Attic provide the global access and global access, and provide the storage, in particular nearline archive storage for certain fees. So currently, the cost is about $20 per terabyte per year, but the data is duplicated at the main site as Omaha and the silo at the Lincoln. So in the next section, then you will get more details about the HCC storage options. And for the file transfer, we provide the traditional access through the CLI interface, including the scopy, SDP, and rsync. And also we provide the GUI tools like Win scopy and also the corresponding interface to these CLI tools. And we also provide Globus Connect. So this is a service developed by University of Chicago. So this is a web-based user portal, allow you to conduct the file transfer before the established endpoints and personal machines. So this tool and service has been widely used by the other universities and the national labs and the other research institutions. So this allows the user to easily configure the shared endpoint and to conduct the collaboration on data sharing and management. And moreover, we also integrate HCC Globus with UNL OneDrive. So for the UNL users and they can use the Globus Connect to transfer their data from the OneDrive to HCC storage. So this diagram showing the web interface of Globus Context. And you might see this follows the traditional UI design for the data transferring. Then you can use the drag and drop to conduct intuitive data transferring from the different endpoints. Okay. So based on this facility, we also provide different support. For the detailed documentations, you can always go to the hcc.unl.edu/docs, so which provide all the aspects of HCC. Examples of traditional usage of HCC also can be found on our GitHub site. And for any help, and you can always email us at hcc-support@unl.edu. And we also conduct open office and Tuesday and Thursday, twice every week from 2 to 3 p.m. And currently we hold from Zoom. And if needed, you can always set up the one-on-one appointment. And we will be very happy to meet with you and discuss the topic or the question you have and provide any support. And we also provide the different training and outreach activities, and including HCC workshops, apart from the Kickstart. So currently we hold on every 4th semester. We also have the June workshop series, so which is typically conducted in every June. And we also have the different carpentry effort, including the software carpentry workshops. And typically we introduce Python and R. As I mentioned, based on request, we also provide classroom and groups tutorials. And if you need it, please contact with us, and we will be very happy to provide the support. So finally, I would like to thank our university, Nebraska Research Institute, and OneIT, and NSF, EPSCO, DOE, and NIH for their support to make HCC more successful. Okay, thanks.